Hello, and today we're going to talk about approximating a binomial distribution with a normal distribution. So back in year 12, in the first year of your course, you learnt about the binomial distribution and you learnt that a discrete random variable is binomially distributed with a number of trials n and a probability of success in each trial p if certain conditions were met. So, for instance, we had that there had to be a fixed number of trials, n. We knew there had to be either a success or failure on each trial, and the probability of success or failure had to remain constant for each of those trials. And we learned that each of the trials had to be independent of each other. So, a classic example of a binomial distribution would be throwing a coin and counting the number of heads that showed. Every time you throw a coin, the outcome is independent of previous times. If it's a standard unbiased coin, then the probability of throwing a head each time is consistently 0.5. And of course, depending on how many times you throw the coin, that gives you n, your fixed number of trials. Now, depending on the size of n, you learnt that you could look in the back of your textbook for the binomial cumulative distribution tables. You also learnt how to use the binomial distribution function on your calculator, which was under option 7 here and going down to number 1 on the second screen, or number 4 on the first screen to work out the probability of an individual outcome. But in certain cases, particularly where n is very large, and generally, we're talking kind of over 50, mainly because the binomial tables go up to n is 50, although large is a rather subjective concept. So the larger n is, the better what I'm about to tell you works. But also, if the probability is close to 0.5, so I've got approximately equal to there, then your binomial distribution can actually be approximated by a normal distribution. And in that normal distribution, we have that the mean is the same as the mean of the binomial distribution, which is NP, and the variance is the same as the variance of the binomial distribution, which is NP1 minus P, which gives us, of course, that the standard deviation would be the square root thereof. So what we're saying here is if you have a large number of trials, and particularly if your probability of success in each trial is close to 0.5, then something kind of like this happens. The value around the mean occurs the most, and then to either side of the mean, a little bit less, and either side of that a little bit less again, but at the same rates. So you end up with something very close to a symmetrical distribution. Now, if P moves away from 0.5, this becomes less and less symmetrical. And if n gets smaller, then these heights here don't display quite so much of a bell shape. So in order for this binomial distribution to fit roughly the bell shape, you do need both of these conditions ideally. And the better each of those conditions is to this, the more this fits the bell-shaped curve, and the more we can approximate our solutions to the binomial with a normal distribution instead. So let's have a look at an example here. We are told that we have a biased coin, and on this biased coin, the probability of throwing a head is 0.53. So this coin is flipped 100 times, and we record the number of x's. So let's make a note of that, shall we? We'll say let x be the number of heads, which means that we're saying that x will fit a binomial distribution with 100 trials and the probability of success each time as 0.53. So part A, which asks us to write down a binomial model for this test, is that, defining x and writing down its distribution. So part B says, why can this distribution here be approximated well with a normal distribution? The normal distribution being this one here. Well, the reason that can work is because n is large, 100, and p is close to 0.5. So the normal distribution should fit this quite well. We've got to then find the values of mu and sigma that we would use in this approximation. So we'd say that mu, that's np, so that's 100 times 0.53, so that gives us 53. And let's start with the variance, sigma squared, that's going to be np1 minus p. NP we've already worked out was 53. 1 minus P is 1 minus 0.53 or 0.47. So that gives us a variance of 24.91. So we have a standard deviation of the square root of that, which is 4.99, and that's to 3 significant figures. So we are approximating this distribution, x, with y, which is a normal distribution, with mean 53 and variance 24.91. Now, you can use these approximations to work out probabilities, but before you do that, I need to talk to you about the concept of a continuity correction, because we have one little kind of blip, if you like, that gets in the way when we are trying to work out answers to a discrete distribution, but using a continuous distribution, because of course discrete distributions take particular individual values, whereas continuous ones can take any value along this line. So let's just quickly very roughly draw ourselves a relatively symmetrical looking binomial distribution. So we'll make the mean here around about 7, and then as we come down each side, we're going to remain symmetrical, something a bit like this. So we've got ourselves a pretty symmetrical looking distribution there, which means we can approximate it with a normal distribution. So I've drawn the normal distribution curve on there. Now let's say for this distribution I wanted to work out, say, the probability that x is greater than or equal to 5. So on my binomial distribution, I would be shading in these bars here, all the way to the end. Now look at this though. The bar that covers the value 5 actually starts at the lower bound of 5 here, which is 4.5. So when we approximate it, we say that that would be approximately equal to the probability that y, which is the normal distribution, is greater than 4.5. We would use the lower bound of this value 5 here. Let's do a few more examples of these, shall we? If you had to work out, say, the probability that x is just greater than 5, don't forget x here is the binomial discrete distribution. Now, because this is greater than, not greater than or equal to, the first thing we do is turn it into a greater than or equal to statement. So that's the same thing as saying x is greater than or equal to 6. Once you've got the equal to bit here, you're then going to use the lower bound of this number because we're going above it. So we're saying that that's approximately equal to the probability that y is greater than 5.5. Let's imagine we wanted to go less than something. So let's take another one like this. What's the probability that x is, let's go less than 4? Well, that hasn't got the equal to part on the inequality. So let's change that into the probability that x is less than or equal to 3. So on this diagram here, less than or equal to 3, let's do it in a different colour, would be that bar, that bar, that bar, and down. But this bar at 3 includes all the way up to the upper bound of 3 there, which is 3.5. So we would approximate that with the probability that y is less than 3.5. And this, where we take the upper or the lower bounds here, this is called a continuity correction. Let's do one more example. Let's take something like the probability that x equals 9, because on a discrete random variable you can equal a particular number. So that means we need to go to the lower bound of 9 and the upper bound of 9, and we approximate this with the probability that y is between 8.5 and 9.5. And you can see that by looking at the bar here that covers 9, and you can see that it goes down to 8.5 and up to 9.5. So whenever you're working out any of these questions now, doing a normal approximation, you have to remember to do a continuity correction first. So let's have a look at example 12. We're told that we have a binomial random variable with n 150 and p 0.48, and it's approximated by a normal random variable. Let's just quickly work out the parameters of this normal variable. Mu here is np, so we've got 150 times 0.48, which gives me 72, and the variance is worked out by np, which is 72, multiplied by 1 minus p. So that gives me 37.44 for the variance. Now, if you look in the book, you will see that it doesn't give you 37.44 explicitly after the comma here. What it does is it writes that as 6.12 squared. So I've given the exact value here of the variance, but the book writes it as the standard deviation squared. So let's just make a note of that, 6.12 squared. So we are asked to first of all work out, using the approximation here, the probability that x is less than or equal to 70. So it's already got the equal to part on it. Let's apply our continuity correction. So that's approximately the same as the probability that this normal distribution gives us a variable, the chance of it being less than 70.5. Now let's go to our calculator. We want normal cumulative, really low lower bound as always, upper bound 70.5, sigma was 6.12, mu is 72, and that gives me a probability of 0.4032. to 4 decimal places. Next, we have got to work out the probability, or approximate, sorry, the probability that x is between 80 inclusive and 90 exclusive. We're going to rewrite this first so that this inequality is inclusive. So that's the probability that x is between 80 and 89. Now we're going to approximate it with a continuity correction. So that's approximately the probability that y is between lower bound of here, 79.5, and upper bound of here, 89.5. Now, to work this out then, we again are going to come to our calculator, but this time our lower value is 79.5 and our upper is 89.5, keeping the same parameters, and we get 0.1081 to 4 decimal places. So we've got the basic idea. Let's have a look at a contextual question. So for this one, we are told that for a particular type of flower bulb, 55% of them produce yellow flowers. We're told that 80 bulbs are planted, and this is our random sample. We've got to work out the chance is that of these 80 bulbs, 50 of them are yellow, But we've also got to approximate it using a normal distribution, and then we've got to work out the percentage error. So how accurate is this approximation compared to the actual probability? So let's start off then by defining our variable x. We're going to let x be the number of yellow flowers, and we'll write down what the binomial distribution for x is. So we had 80 bulbs planted, and the probability of it being yellow each time is 0.55. So to find the probability that x equals 50, we can go to the calculator for this, can't we? So we'll go to our distribution, and we want binomial probability distribution. X is 50, n is 80, p is 0.55, and that gives us a probability of 0.03651. So let's now have a look at our approximation. We're going to say that x can be approximated by a normal distribution where mu is np and sigma squared, or the variance, is np1 minus p. So that means that y would be a normal distribution. We have np is 80 times 0.55, that's 44. And np, which is 44, times by 1 minus p, which is 0.45 of course, gives us 19.8 for the variance. Let's make a little note in brackets that sigma squared, that's 19.8. So sigma, just in case we need to think about it at all, is 4.45 to 3 significant figures. So we're trying to work out the probability that x is 50. So that's going to be approximately the same as the probability that y is between, apply our continuity correction, the upper and lower bounds of this are 49.5 and 50.5. So let's work out that one on our calculator. Normal cumulative, and we want the lower as 49.5, upper as 50.5, sigma was 4.45, and mu is 44. And we get our probability coming out as 0.03619. Now that's quite close, 0.03651 and 0.03619. So what I need to do now is answer the last part of the question, which is calculate the percentage error incurred when we use this compared with this one. So the original one is the larger. The percentage error is going to be the difference between them. Divided by the original and times by 100. So let's work that out. And we get I think I've mistyped something. Let's go back and check it. 0.03651 minus 0.03619 over 0.03651 times 100. No, all right. We get an error of 0.88%. Now, the reason I thought I'd made a mistake there actually is the book says 0.92%, and I think I know why my answer is different to the book, and it's because when I put this one in, I wrote down 0.03619, and I'm wondering if I just made a rounding error or if the book should have written the 9 there instead. Let's check. So if we just go back into our distribution, normal, cumulative, lower is 49.5, upper is 50.5, sigma is, let's type it in as the square root of 19.8 and use it exactly. Yeah, definitely 4.45, so I was okay there. And mu is 44. 0.03618. Yep, that was my mistake. So we'll change that to an 8, and I bet if we go back here now and change that to an 8, we'll be fine. Let's check. Goes to show what a tiny difference this can make to the final value. 0.03651 minus 0.03618 over 0.03651. Times by 100. It's still different to the book. I reckon the book's made a mistake. That's coming out now with my change as 0.90%, and the book still says 0.92. Do you know what? Just before I finish the video, I'm going to check their calculation. 3651 minus 0.03618 over 0.03651 times 100. Yeah, the book has made a mistake. It's not 0.92%. It goes to show, actually, that a tiny little rounding error can quite significantly change your answer, but it also goes to show you need to double check these books. Anyway, you now know enough to complete exercise 3F. Have a go, see how you get on. Good luck.